Hi, I welcome you all to this session on problem solving in semiconductors. I am Dr. Yunus Cherusha, an assistant professor of physics. Today, we are going to solve problems and make it an interesting session. Let us begin. Before we proceed to solve problems, let us try to recollect a few formulae which are important to solve these. The first is resistivity, rho, which is inversely proportional to the conductivity sigma. Intrinsic conductivity sigma I is given by NIE into mu E plus mu H, where Ni is the intrinsic carrier concentration, E the charge of an electron, mu E and mu H being the mobilities of the electron and hole respectively. Also, sigma is given by a constant times e to the power of minus e by 2kT, where E stands for the band gap energy, K the Boltzmann constant, and T the absolute temperature. The intrinsic resistance Ri is given by rho L by A, where L stands for the length of the material and A its area of cross section. The law of mass action for an intrinsic semiconductor is given by the product of the electron concentration N and the hole concentration P, which is equal to the square of the intrinsic carrier concentration Ni square. The current in an intrinsic semiconductor I is the sum of the hole current as well as the electron current. The conductivity in an n-type semiconductor is given by sigma n equals E into Ne into mu E. Similarly, for a p-type semiconductor, sigma p is equal to E into Nh into mu H. The Hall coefficient RH is given by VHB by IHB, where VH stands for the Hall voltage, B stands for the breadth of the material, IH the Hall current, and capital B standing for the transverse magnetic field. The Hall voltage VH is given by RH IHB by T, where T stands for the thickness of the material. Finally, the Hall mobility is given by mu H is equal to RH sigma, where sigma stands for the conductivity of the material. The first problem. Find the resistance of an intrinsic germanium rod 1 centimeter long, 1 millimeter wide and 1 millimeter thick at 300 Kelvin. Assume conductivity of germanium to be 2.32 ohm inverse meter inverse. The solution is C. We find this from the formula of intrinsic resistance Ri equals rho L by A. We substitute the appropriate values of the length, the conductivity and the area of cross section, and we find the answer to be 4310 ohms. The second problem, a semiconducting material 12 mm long, 5 mm wide and 1 mm thick has a magnetic flux density of 0.5 Weber per meter square applied from the front to the back perpendicular to the largest faces. When a current of 20 milliamps flows lengthwise through the specimen, the voltage measured across its width is found to be 37 microvolt. What is the Hall coefficient of this semiconductor? The solution is B. The formula for the Hall coefficient RH is VHB by IHB. On appropriate substitution of the various given parameters, we find the Hall coefficient to be 3.7 into 10 power minus 6 meter cube per Coulomb. Problem 3. The intrinsic carrier density at room temperature in germanium is 2.37 into 10 power 19 per meter cube. If the electron and hole mobilities are 0.38 and 0.18 meter square per volt per second respectively, calculate its resistivity. Assume sigma I to be 2.12352 ohm inverse meter inverse. The answer is D. We find this from the formula of resistivity given by 1 by sigma I, where sigma I is given by NIE into mu E plus mu H, and substituting the respective given data, we find rho I, the intrinsic resistivity, to be 0.4709 ohm meter. Problem 4. A silicon plate of thickness 1 mm, breadth 10 mm, and length 100 mm is placed in a magnetic field of 0.5 Weber per meter square acting perpendicular to its thickness. If 10 power minus 3 amp current flows along its length, calculate the Hall voltage developed. If the Hall coefficient is 3.66 into 10 power 4 meter cube per Coulomb. The answer is A. The Hall voltage is given by VH is equal to RH IH B by T. Substituting the given data, we obtain the Hall voltage to be 1.83 millivolt. Problem 5. The conductivity of germanium at 20 degrees Celsius is 2 ohm inverse meter inverse. What is its conductivity at 40 degrees Celsius given the band gap is 0.72 eV? The answer is B. We know the conductivity is given by sigma is equal to a constant times e power minus e divided by 2kT. Since we have two different conductivities, one at 20 degrees Celsius and the other at 40 degrees Celsius, we assume sigma 1 to be that at 20 degrees Celsius and sigma 2 to be at 40 degrees Celsius. We substitute the given data in the given formula there, and we find for the conductivity at 40 degrees Celsius, which is sigma 2, to be 1.0002 ohm inverse meter inverse. Problem 6. The Hall coefficient of a specimen is 3.66 into 10 power minus 4 meter cube per Coulomb. If its resistivity is 8.93 into 10 power minus 3 ohm meter, what will be its mobility? The answer is D. Mobility mu H is given by RH sigma. We substitute the data given and we find the Hall mobility to be 0.04 meter square per volt per second. Problem 7. Pure silicon at 300 Kelvin has equal electron and hole concentrations of 1.5 into 10 power 16 per meter cube. Doping by indium increases P to 4.5 into 10 power 22 per meter cube. What is N in the doped silicon? The answer is C. We know from the law of mass action, Np is equal to Ni square, and from that we find small n. Substituting the data which is already given, we find N to be 5 into 10 power 9 per meter cube. Problem 8. In a semiconductor, it is observed that 3/4 of the current is carried by electrons and 1/4 by holes. If the drift speed is 3 times that of the holes, what is the ratio of the electrons to the holes? The answer is A. In an intrinsic semiconductor, the total current is given by IE plus IH, and from the problem given, IE is 3/4 of I and IH is 1/4 of I, and we have also been given the drift velocities to be V to be 3 times VH. Substituting, we finally find the ratio of the electron and hole concentration to be 1:1. Problem 9. If the number of electrons in a semiconductor is 5 into 10 power 20 per meter cube and mobility is 0.135 meter square per volt per second, find the resistivity of the semiconductor. The answer is A. The conductivity is given by E times Ne into mu E, which we substitute in resistivity and find the resistivity to be 0.0926 ohm meter. The last problem, find the resistivity of an intrinsic semiconductor with intrinsic concentration of 2.5 into 10 power 19 per meter cube. The mobilities of the electrons and holes are 0.4 meter square per volt per second and 0.20 meter square per volt per second respectively. The answer is C. We find out the conductivity given by Nie into mu E plus mu H, from which we find the resistivity rho I to be 0.4166 ohm meter. Thank you for making this session a really interesting one. Hope you liked it, and this will help you to solve many such problems which will be useful when it comes in the time of an examination. If you like this video, please subscribe